Welcome to this lecture of calculus. In this lecture, we shall discuss the Taylor's theorem. Taylor's theorem is a powerful result that allows us to approximate a differentiable function by a polynomial. So we have an approximation. Now, as we are approximating a differentiable function by a polynomial, so there must be some error. The theorem actually also provides a precise formula for that error, or we also call that error as a remainder in this approximation. Now here in this lecture we shall discuss the Taylor's theorem with two different forms of remainders. One type of remainder is called the Lagrange's form of remainder, and another remainder that we will discuss here that is known as the Cauchy's form of remainder. So we begin by defining the Taylor's polynomial with these two different forms of remainders. Now first of all, let f be a function such that its first n derivatives exist in the neighborhood of a point A. The Taylor polynomial of degree n for f at A is given by Pn of x, which is defined as f of A plus x minus A divided by 1 factorial f dash of A plus x minus A whole square divided by 2 factorial f double dash of A plus so on plus x minus A power n divided by n factorial f and the derivative at A. So this is how we define the Taylor polynomial approximation of a function which is differentiable at least n times. Now let's mention the Taylor's theorem here. Taylor's theorem with Lagrange's form of remainder. The statement of the theorem goes like this. Let f be a function such that its first n derivatives are continuous on a closed interval a comma x, and its n plus 1th derivative exists on the open interval a comma x. Then there exists at least one number c, in the open interval a comma x, such that f of x is equal to Pnx, which is the Taylor's polynomial of degree n as defined above, then plus Rn of x, where this Rnx is the remainder, where Rnx is the Lagrange's form of remainder, given by Rn of x is equal to Fn plus 1 at c divided by n plus 1 factorial into x minus A power n plus 1. So this is the Taylor's theorem with Lagrange's form of remainder. So this approximates a polynomial f of x with Pnx plus Rnx, where the Lagrange's form of remainder Rnx is defined as Rnx equal to Fn plus 1c by n plus 1 factorial into x minus A power n plus 1. Now first here we take an application of the Taylor's theorem with Lagrange's form of remainder, and then later on we shall discuss about the Taylor's theorem with Cauchy's form of remainder. So now here we take an example. So here in this question we have many steps to follow. First of all, we will evaluate the degree 3 Taylor polynomial, that is we need to evaluate P3 of x at a equal to 0. Then we will find the approximate value for log of 1.1 using this degree 3 Taylor polynomial. Now since this is just the approximation, this P3x will be the approximation of log of 1 plus x. Therefore, there will be some error involved in the evaluation of log of 1.1. And then we will also find the upper bound for the error which is involved in the approximation of log of 1.1. So we take up the solution. First of all, we mention the Taylor's polynomial. We have the Taylor's polynomial of degree n is Pn of x, which is equal to f of a plus x minus A by 1 factorial f dash of A plus x minus A whole square divided by 2 factorial f double dash of A plus so on plus x minus A power n by n factorial f n a derivative at E. So this is the Taylor's polynomial of degree n. Now here in the question we are given to evaluate the third degree Taylor's polynomial. So hence the third degree Taylor's polynomial is P3 of x, which is equal to f of a plus x minus a by 1 factorial f dash of a plus x minus a whole square by 2 factorial f double dash of a plus x minus a whole cube divided by 3 factorial f third derivative at e. So this is the third degree Taylor's polynomial. But again we are not going to evaluate this polynomial at x equal to a, but we need to evaluate this at x equal to a equal to 0. So therefore for a equal to 0, third degree polynomial is, the Taylor's polynomial is P3 of x, which is equal to f of 0 plus x divided by 1 factorial f dash of 0 plus x square divided by 2 factorial f double dash of 0 plus x cube divided by 3 factorial f triple dash of 0. Now let's first of all evaluate what is f of 0, f dash 0, f double dash 0 and f triple dash 0. So let's call this equation as equation number 1. So now we have f of x is equal to log of 1 plus x. So this gives f dash of x is equal to 1 divided by 1 plus x, because the derivative of log of 1 plus x equal to 1 by 1 plus x. So now this further gives the second derivative at x, which is equal to 1 divided minus 1 divided by 1 plus x whole square. And similarly this gives the third derivative at x is equal to, so this should be 3 divided by 1 plus x whole cube. So these are the first three derivatives of f of x. Now we need to evaluate f of 0. So this implies f of 0, that is equal to log of 1, which is equal to 0. So now this gives us f dash of 0. Now obviously that is equal to 1. Now this derivative gives us f double dash of 0. Now this is equal to minus 1. And here we get the third derivative at 0, that is equal to 3. So we are done with the calculations. Hence the third degree Taylor polynomial is P3 of x. This is equal to, now first of all f of 0, but f of 0 is equal to 0, then plus x divided by 1 factorial f dash of 0, that is equal to 1, plus x square divided by 2 factorial f double dash of 0, that's equal to minus 1, plus x cube divided by 3 factorial f triple dash of 0, that's equal to 3. So finally this becomes x minus x square divided by 2 plus 2x cube. So this is the third degree Taylor's polynomial for the function log of 1 plus x at a equal to 0. So we are done with the first step for evaluating the Taylor's polynomial of third degree. Now on similar lines we can find the Taylor's polynomial of fourth degree or fifth degree or any higher degree. Now the next question involved in our example is to evaluate the approximate value of log of 1.1, and then finally we shall find the approximate or the upper bound for the Lagrange's form of remainder. So now we go into the step number 2. To find the value of log of 1.1, so we chose x is equal to 0.1. Now how do we choose x equal to 0.1? That we shall see here. We have the function log of 1 plus x. This is our given function. Now we need to evaluate the value of log of 1.1. Now we can write this log of 1.1 as log of 1 plus 0.1. Now if we compare 1 plus x with 1 plus 0.1, so we can clearly see we must choose this x as 0.1. This is how we evaluate the value of x. So therefore approximate value of Therefore, approximate value of log of 1.1 is equal to p of 0.1, because we have evaluated the value of x to be equal to 0.1. So we substitute this x equal to 0.1 in this Taylor polynomial here. So therefore we obtain this is equal to 0.1 minus 0.1 whole square divided by 2 plus 2 into 0.1 whole cube. Now using the calculator we can see this is equal to 0.096. Now finally we evaluate the error or the upper bound in the error of Lagrange's form of remainder. The error in this approximation is given by R3 of x, which is now defined as the fourth derivative at some point c divided by 4 factorial into x power 3 for some c belonging to the open interval 0, x. Now we already have the third derivative of f. Now we evaluate the fourth derivative. Now we have the fourth derivative f4 of x. Now as we already have the third derivative is given as 3 divided by 1 plus x cube, so fourth derivative will be minus 12 divided by 1 plus x power 4. So this is minus 12 divided by 1 plus x power 4. So for x equal to 0.1, the error is R3 of 0.1, which is equal to the fourth derivative at c divided by 4 factorial into 0.1 power, this must be 4 here, so this is power 4. So therefore this is equal to, now the fourth derivative at c, that is equal to minus 12 divided by 1 plus c power 4 divided by 4 factorial into 0.1 power 4. Now after calculations we get this is equal to, now 4 factorial is equal to 24, so 12 by 24 is minus 1 by 2, so this will be equal to minus 1 divided by 2 into 1 plus c power 4 into 0.1 power 4, that is equal to 0.0001. Now we evaluate the absolute value, so this implies this modulus of R3 of 0.1. So this is equal to 1 divided by 2 into 1 plus c power 4 into 0.0001. Now since we need to evaluate the upper bound of this error, so we need to find the maximum value of this expression on the right hand side. So to find upper bound for R3 of 0.1, we must find the smallest value of the expression in the denominator. So the expression in the denominator is 2 into 1 plus c power 4. So we must evaluate the minimum value of 1 plus c power 4 in the interval 0 to 0.1. So because now if we have an expression of this form, like which is, suppose if we have an expression of the form 0.0001 divided by 2 into 1 plus c power 4, now this expression will be maximum provided this denominator is minimum. So therefore we need to evaluate the minimum value of 1 plus c on the interval 0 to 0.1. Now one obvious thing is that 1 plus c power 4 into 2, this is minimum if this c is minimum in this interval, because as we increase c, so 1 plus c power 4 will increase. So therefore for the least value of c in the interval that is equal to 0, we will get the smallest value of 1 plus c power 4. So thus we must have c is equal to 0. And for c equal to 0, we have this R3 of 0.1. This is always less than or equal to 0.0001 divided by 2. Now this is equal to 0.00005. So therefore this is the approximate error in the evaluation of log of 1.1 using the Taylor's polynomial of degree 3. Now we evaluate the Taylor's theorem with Cauchy's form of remainder. We begin with the statement of Taylor's theorem with Cauchy's form of remainder. The statement goes like this. So actually the Taylor's theorem with the Lagrange's form of remainder and Taylor's theorem with Cauchy's form of remainder have exactly the same expansion. F of x is equal to Pnx plus Rnx, but the difference only lies in the remainder term Rnx, which is different in the Lagrange's form of remainder and is defined in this way as given here in the Cauchy's form of remainder. So we just take up an example to derive the error or take an application of the Taylor's theorem with Cauchy's form of remainder. So here we have an example. Since we have already evaluated the Taylor's polynomial P3x in the previous example, so we shall just pick up its part, which is P2 of x. So in the solution, we have P2x is equal to x minus x squared divided by 2. So then log of 1.1, that is equal to P2 of 0.1, which is equal to 0.1 minus 0.1 whole square divided by 2, and this is equal to 0.095. Now let's evaluate the error in this approximation using the Cauchy's form of remainder. Now the remainder Rnx in Cauchy's form is given by Rn of x is equal to fn plus 1 at some point c divided by n factorial into x minus c power n into x minus a. And here in this case we have a equal to 0 and x equal to 0.1. Now here we have x is equal to 0.1, a is equal to 0, and since we are going to evaluate the remainder R2 of x, so we have n is equal to 2. Therefore the error is R2 of 0.1. This is equal to f double dash at c divided by 2 factorial into 0.1 minus c whole square into 0.1 minus a, that's minus 0. So this becomes, this is equal to, now the second derivative of the log of 1 plus x is equal to 2 divided by 1 plus x square. Now using that second derivative, we obtain this value is equal to 2 divided by 1 plus c whole cube into 1 divided by 2 factorial, that's 1 divided by 2 into 0.1 minus c whole square into 0.1. So this becomes, this is equal to 0.1 minus c whole square divided by 1 plus c whole cube into 0.1. Because this 2 and 2 is cancelled and the remaining is now written in simplified form. This is for some c belonging to a comma x. Now a is equal to 0 and x is equal to 0.1. Now in order to find the upper bound for this error, we need to evaluate the maximum value of this expression 0.1 minus c power 2 divided by 1 plus c whole cube into 0.1, and for clear reasons we just need to evaluate the smallest value of this denominator so that the whole expression is largest. Now clearly the largest bound, or we can say the upper bound for R2 0.1 is obtained at c is equal to 0, because c equal to 0 is the value where 1 plus c whole cube is smallest. Hence the error is R2 of 0.1, we can take the modulus here, this is less than or equal to 0.1 minus 0 whole square whole divided by 1 plus 0 whole cube into 0.1. So therefore this is equal to 0.1 whole square into 0.1, which is actually 0.1 whole cube, and this is 0.001. So this is the error given by the Cauchy's form of remainder in evaluating log of 1.1 using the Taylor's expansion, but using the Cauchy's form of remainder.